Hello, I'm Joaquin Joya, and today I'm going to explain you how to calculate surface areas of 3D shapes defined by three different domains using integration. So, let's take a look at the first domain. It is defined in terms of x, y, and z in r cubed. X squared plus y squared is less than or equal than 1. This means that it is a circle of radius from 0 to 1 in center 0, 0. And here it says that z equals 0, which means that this circle is in the xy plane. Okay, next. Again, it's defined in x, y, z in r cubed, and again x squared plus y squared equals 1. It also says that z has to be greater than 0 but smaller than equal than 3. This means there's going to be a circle of radius 1 constant that goes from 0 to 3. If we put all this data together, we have a cylinder of radius 1 and height of 3. Okay, next surface. Again, x, y, z in r cubed. Then it says z minus 4 equals minus x squared plus y squared. And that z goes from 3 to 4. Okay. We will explain later how to know which type of shape this domain defines. Okay, so let's start calculating the surface for the first domain. The first thing we want to do is to pass this into polars, because if we were to use Cartesian coordinates, they're not a very good match when working with circles. So we need to pass it to polars. How do we do this? Very simple. Polars are defined in terms of rho and in terms of theta, which is our angle, in r cubed also. X squared plus y squared will be rho squared. So rho will go from 0 to 1. So rho in the interval from 0 to 1. As in this domain theta does not appear, it means that this is a revolving surface, which means that theta can take any value from 0 to 2 pi. So theta is in the interval between 0 and 2 pi. We could put z also, but as it's 0, it's not important, so we're going to leave it like this. Okay, so what do we do now? We need to do a double integration ds, differential of surface. Okay, so how do we know what our limits of integration are going to be? Well, we've got them right here. Rho has to go from 0 to 1 and theta from 0 to 2 pi. So we start here with theta 0 and 2 pi, and then another integral from 0 to 1. What will ds be? As we are in polars, we need to put a rho here. This is the Jacobian. It is really important to put it every time you pass from Cartesians to either polars or cylindrical. It will be differential of rho and the theta. So here we can integrate directly this, it is independent from this. So the integral from 0 to 2 pi of the theta will be 2 pi times the integral of this from 0 to 1. This will be rho squared, so a power up, and divided by new power over 2 from 0 to 1. If we substitute in this 1 and 0, we'll get 1/2. So this means that it's 2 pi times 1/2, which equals pi. So this is the surface area of our first domain. Okay, let's take a look at the second domain, S2. In this case, it will be more convenient for us to put this, not polars, but in cylindrical coordinates, as Z is defined. So, how are cylindrical coordinates defined? They are defined in terms of rho, theta, and Z in r cubed. So, rho in this case is 1, as the radius of this circle is constant and is equal to 1. Okay. Again, as theta does not appear here, it means that it's a Rhoean surface. So theta can take any value from 0 to 2 pi. And finally, it says that Z goes from 0 to 3. So we put it here, in the interval from 0 to 3. Okay, how do we find the surface area of this domain? Again, another double integration. Now, what will our limits of integration be? Well, we're going to start with theta, that will be from 0 to 2 pi, and Z from 0 to 3. So again, here, 0 to 2 pi, and Z from 0 to 3. Again, as we've passed from Cartesian coordinates to cylindrical, we need to put the Jacobian, which is rho, dz, which is this one, and d theta. In this case, rho, as we put here, it's constant and it's equal to 1. So this will be 1. So now it's a really simple integration. There will be the integral of this times the integral of this. It will be just 2 pi times 3, which is 6 pi. So this is our second surface area. Alright. Now let's go on to third domain, S3. Previously we were talking about how do we know what the shape of this strange, in more or less, domain is going to be like. So, as we've seen before, x squared plus y squared is rho squared. So I'm going to put it here, rho squared. Alright, so we're going to put this whole equation, and we're going to pass this to the other side. So Z will equal to 4 minus rho squared. Alright, so to know the shape of this domain, we will plot a rho against Z axis. So rho and Z. So now let's put some values and see what a line will be like. So for example, when Z equals 0, what is rho? Rho will equal 2. So Z0, rho 2, somewhere here. 2. First point. another point. When, let's see, row equals 0, what is z? Z equals 4. So row 0 and z 4. This is our other point. And let's take one more value, like when row equals 1, what will z be? Z will be 3. So this will be, so 1's here, 3 will be somewhere here, so here. If we join these 3 dots together, we'll get this kind of curved line. As we said before, this is a revolving surface. So if it will revolve in this axis, in the z-axis, so how will this look in 3 dimensions? Well, it will look something like this. We'll do a graph, a 3D graph. X, Y, Z. And let's see, let's take that. It says it goes, Z goes from 3 to 4. So let's say 3 is here and 4 is here. 3 and 4. So if we revolve this in the Z axis, it will look something like this. Okay, so it will look like a bowl upside down. Yeah. Okay, and now, how do we calculate the surface of this shape? Well, we can't calculate it directly. So what we do is we use a projection coefficient. This projection coefficient, what does is calculates the surface of the projection of this figure. So what will the projection of this figure be in the xy plane? It will be a circle here. So this is like if you put a light from here, what will the shadow be in the xy plane? It will be something like that. Well, this is meant to be a circle of radius 1. Okay? That's like the shadow. And we're going to call this circle D. Now, what will the domain of D be? Let's take a look. D, defined in x, y, and z, in r cubed, will be, as it's a circle in center 0, 0, x squared plus y squared is more or equal than 1. And also, well, z equals 0. So it will be kind of the same as our first domain. So if we want to put it in polars or cylindricals, it will be in terms of rho, t, in this case we're going to put z, so we're going to put in cylindricals in r cubed, when rho goes from 0 to 1, theta from 0 to 2 pi, and z equals 0. So it will be our domain of the projection of this figure in the xy plane. Now, the projection coefficient has a formula, which is as follows. We're going to call it P as projection, PC. It's the root of 1 plus gx squared plus gy squared, where gx is the derivative of this in terms of xy, the derivative of x and the derivative of y. So let's work here. G of x. Well, before putting this, we need to put this function in terms of x and y. So we need to leave z alone. So z, which is the same as f of xy, will equal 4 minus x squared minus y squared. Okay? So g of x is the derivative in terms of x of 4 minus x squared minus y squared, which equals minus 2x. Then gy is the derivative in terms of y of the same, 4 minus x squared minus y squared, which equals minus 2y. Oops, 2y. So now we substitute these two values into the formula. It will be 1 plus 4x squared plus 4y squared. As we see here, we have an x squared and a y squared, which we previously said that this was rho squared. So we can rewrite this as the root of 1 plus 4 times rho squared. It will be much simpler. Okay. Now we need to integrate this for our third domain. So, how would this go? It will be a double integral of what we've just done, 1 plus 4 rho squared. What will our limits of integration be? Well, there will be let's see rho, what, theta from 0 to 2 pi, and no, this is the other one. Let's see. Yeah. Theta will go from 0 to 2 pi as it's a revolving surface. Oh yeah, of course, it's this one. We need to integrate this domain, so rho from 0 to 1 and theta from 0 to 2 pi. So again, 0 to pi and 0 to 1 of this 1 plus 4 rho squared, and as we've passed from Cartesian to cylindricals in this case, we need to put the Jacobian, which is rho. Then d rho and d theta. Okay. So now, how do we integrate this? Well, we know that the integration of f prime, which is the derivative of f, times f to the power of a, equals 1 over a plus 1 times f to the power of a plus 1. In our case, f is 1 plus 4 rho squared, so the derivative of this, f prime, is 8 rho. So what do we need here so that we have both the function and the derivative of this function. We need to put to this row times it by 8. Now we have the function and also the derivative of this function. And as we've multiplied here by 8, we need to divide here by 8, so it stays the same. Now, what is the derivative, the integral of a square root? The integral of f to the power of a half is f, then raise one power up, it will be 3/2, and times, well, it will be divided by this, that we can change to 2/3. So this here will be the integral. Well, we can pass the 1/8 outside the integral as it's a constant and it will not affect the integration. So 1/8, the integration of 0 to 2 pi times 1 plus 4 rho squared. This is times by 2/3. So I'm going to put this brackets instead. I'll put square brackets here. And to the power of 3/2. And now from 0 to 1 d theta, because we haven't integrated this part yet. Of course we can integrate this whenever we want, as it's completely independent of this thing. So it will be 1/8 times 2 pi times, we need to substitute 1 and 0 into all of this. This will make 2/3 times 5 to the power of 3/2 and 0, so -1. Alright, so we can simplify this a bit. It will get simplified to pi/6 times 5√5 -1. So this will be our last integration. Now, if we want to get the total surface of the whole shape, it's obviously a simple sum of all the integrations we've done. So let's call the total surface ST. It will equal S1 plus S2 plus S3. So S1, we said it was pi, so pi plus S2, which was 6 pi, plus S3, which we said was this, pi/6 times 5√5 -1. And this will equal, let's see, pi/6 times 41 minus 5√5. And this will be the total surface area of our 3D shape.